non-linear and linear, I don't know. So.
Okay, hello everyone, and welcome to this talk. First of all, thanks for the organizers for the opportunity to talk here. So far we have seen a couple of talks concerning applications, so this will be totally something different. I work as a software developer at NAG, and the NAG, if you know or not, is a software company which develops numerical libraries. And the idea of numerical libraries is obviously that people from both academia and industry hopefully can use some of the routines from the library, be it something from optimization or evaluations of special functions or numerical quadratures or something in their projects. And they don't need to reinvent the wheel again. They just can use the stuff, the package they could eventually trust and build upon it. So, it's quite important to hear what people are doing like this, because we need to know what problems are being solved, what solvers are needed, and so on. But I would say that the relationship works both ways. So not only that we listen to customers and or potential clients and asking what solvers do you need and implement it, but it works the other way around as well, that we can say, okay, we think that this algorithm matured enough. Now we put it in the library and use it. And maybe it's something new which you haven't used before, but you could perhaps consider how to reformulate your problems if this particular solver can help in your system. And hopefully it will encourage more applications in that particular area. So, and that's exactly what I'm going to talk about in this talk. I would like to talk about a project which is culminating right now, and it's about getting, in fact, nonlinear semi-definite programming solver to the NAG libraries. So, here is my brief outline. So I won't talk about applications. I will mainly talk about the code, how the problem input looks, and so on. But before, I thought maybe not everyone knows NAG, so in 2 slides I will introduce NAG. Then I will talk about the formulation, the code, and hopefully there will be enough time to show you a couple of examples. Okay, so who is NAG? NAG stands for Numerical Algorithm Group, and actually it's quite useful to look in the history. It was founded in 1970. For me, it's ancient time. There were no personal computers. Microsoft didn't exist. C language was being developed, and they were using something like Algol 60 and Fortran 4. And already in that early time of scientific computation, they recognized the need that it would be quite handy if someone took care of code being developed at universities by experts in the field. So the idea how NAG was founded was, let's collect the software from academia, let's package it up, let's secure that it has proper documentation, that it's tested, that the algorithms are robust, package it up and put it back to people that hopefully they will be able to use it and reuse it. And if you fast forward 40 years, it actually hasn't changed that much. What has changed is that it's not part of the university, but it's self-funded company, and actually it's not for-profit company, which means that if you buy the NAG library, you can have the warm, fuzzy feeling that all the money you spend will be spent again in development, either in-house at NAG or sponsoring some students or external projects at universities. But we are still developing and offering the libraries, so there is still in-house development or development in collaboration with some universities, or there is also contributed code. So if someone thinks that this algorithm needs wider audience or proper implementation, then obviously they are more than welcome to come to NAG and discuss it. Well, the focus is the same. It's more important to get right result slower than wrong result fast. And obviously what has changed since early days are all the bindings. So now you have all the languages to adjust to the user and his environment. In addition to the libraries, there are a couple of things NAG does, so you can know it from high performance computing, or for example, it's NAG Fortran compiler or some LAPEC work or standardization processes on various committees. But enough about NAG. So what happened is that NAG needs to listen to the customer what they need. And there was enough interest that they wanted semi-definite programming solver. And there was enough interest that it would be silly to ignore it. So what happened is that NAG teamed up with University of Birmingham, with Michal Kočvar over there. And as a result, there is an implementation of code which is called Pennon, which is a code for nonlinear semi-definite programming in the NAG libraries. So what does it mean, nonlinear semi-definite programming solver? Well, basically you have pretty general formulation. You assume that you have some functions which are sufficiently smooth. You have objective which can be linear, quadratic, non-linear, even non-convex. You have some inequalities, equalities, and in addition to that, you have a set of constraints on matrix eigenvalues. So here is written that some matrices AK, which somehow depends on X, are negative semi-definite. And obviously this covers all possible formulations. So it covers NLP, it covers linear SDP, or somehow special forms of nonlinear SDP, such as that is not linear anymore, you add some quadratic terms or bilinear terms to the constraints, or even you can go to the higher order and create polynomial matrix inequality semi-definite programming problem. Or you can stick to the general one. Now, you might think, okay, so it's very generic package, so it might not be very good. But actually, if you look at the benchmarks for NLP and linear SDP, where it's actually compared, it's not so bad. So that's one thing. And second thing is this unique blend of constraints that you can suddenly solve things with matrix constraints and with ordinary constraints is actually quite helpful. So what kind of applications can you get? Well, obviously NLP, I won't talk about it. Linear SDP, linear SDP codes are here long enough to attract attention and find its use. So there are plenty of applications in finance, in control theory, in structural optimization or approximations for combinatorial problems. And a quick Google search actually suggests that it's used a lot even in polynomial optimization. So I'm far from expert in polynomial optimization, and I guess everyone else except me knows that, but the main relationship which seemed to be there is that to decide if polynomial is expressible as sum of squares is the same as solving feasibility problem with linear matrix inequality. And this relationship suddenly allows to do approximations for some global minima for polynomials and things like that. So linear SDP has definitely plenty of applications. And there are plenty of codes to solve it. So it's far not just this particular one. But what about nonlinear SDP? Well, the problem is that it's like, I guess, something like an egg and a chicken. So you don't think about formulations which lead to nonlinear SDP unless you know that there is a solver to that. And you don't develop the solver if you don't know that there are applications. But whatever happens, there were applications in structural optimization where the original team around Michal Kočvar changed the code that it actually accepts nonlinear semi-definite programming. And then they were started collecting problems which appear elsewhere, but it's still somehow at the beginnings. So the question is, we have this relatively powerful package, powerful combination of constraints. So what actually it can solve? Is it possible that it would solve your problem in another formulation better or something. But anyway, so far there are applications in structural optimization, in control theory, in finance, that, let's say, example that you want to find nearest correlation matrix, and so you, let's say that the new matrix you are looking for is as close as possible to predefined matrix in Frobenius norm, subject to some constraints, and obviously it needs to be semi-definite and ones on eigenvalues. But you can suddenly add constraints like constrain the condition number of the matrix, or you can say I would like to preserve the structure, or you can bind some elements of the correlation matrix as you want, and others. So the question is, would it be useful if you know that you have the solver? Well, so let's have a look at the solver. PENON stands for Penalty Method for Nonlinear Programming, and actually the name was created before it was able to solve semi-definite programming as well. So main developers are Michal Kutfara from University of Birmingham and Michael Stingl from Germany. And if you want just basic review of the code, so as I said, you need sufficiently smooth functions. Somewhere inside is a hidden Newton method, so you assume second order. You can put in convex and non-convex problems, but obviously you will get only local convergence to the critical point. And again, the combination of nonlinear programming and semi-definite programming makes it kind of unique. So, so suddenly there are more than one code, and actually it's all the same algorithm. So there is the original code PENON and its little brothers for specific applications such as PEN-NLP and PEN-SDP and PEN-BMI. Then there is implementation at NAG library. And then there is one more code which actually might be quite interesting for you, PENLab, and I will get to it very soon. But basically, if you want to compare the codes, then we could say that the original code, it's partly commercial, free for academia or something like that. It's probably richest in the features because all the ideas were done there and the other codes somehow took over and take its own path. NAG implementation, because of certain design features, it was basically done from scratch. It was redesigned, re-implemented. So there was paid more attention to certain details. So certain parts were parallelized, new tricks were introduced. Hopefully it has a nice user interface, hopefully. One request was that it has also reverse communication interface, so it doesn't have any callbacks, but it stops when it needs to evaluate something, goes back to user, ask for the data, and go back and continues where it stopped. And it should be in NAG library, NAG C library Mark 24. So basically we have code freeze in September, then starts implementations, and hopefully later in the year or at the beginning of the year, it should be in the library, and slowly it will get to all other products. But now, what about this last code, PENLab? Well, when I was still under Michal's wing as a student, and we were trying to change the code, we soon found out that it's actually quite tricky to do any development or trial error approach in the main C code. So the idea was, well, can we somehow get rid of all the tricks which makes it complicated, write it in pure MATLAB, and play with that. And that's what we did. So basically, we rewrote it, we kicked out unnecessary tweaks. I will get to it in a bit. And yeah, the idea is that it should be easy to develop new ideas within that, because it's MATLAB. So it should be also easy to play with it, to add examples, because you have all the flexibility of MATLAB. So in this code, there are a couple of interfaces for specific formulations, like linear SDP or bilinear matrix inequalities, polynomial matrix inequalities, for nonlinear programming via AMPL or directly. And you have also this generic interface where you can plug in everything, but obviously it's more work for you to define it. And also there are some applications coded already. So static output feedback, trust topology, optimization, nearest correlation matrix. These are examples somehow to help you start with the code. But basically, the idea is the same algorithm. It's in MATLAB, so you can assume that it will behave differently. It was coded in the way that it's easy to understand, hopefully. So it might run slower, it might run slightly differently, but the behavior will be similar, and still you can solve the composition of the problems NLP and SDP advanced. And when we did it, it actually worked better than we expected. So we said, okay, so maybe we could put it available. So it's available to public under a GPL license, and you can do whatever you want with it if you follow the license, which is pretty open. So to our knowledge, this is probably the only free NLP SDP code combination around. So especially if you have some applications and you want to try something, please get the code. Originally, there should have been already a link to download it from NAG page, but I didn't get to it. So at the moment, if you want it, write me an email. There is the code and technical report which explains what to do with that and so on. And as soon as it's alive on the page, I will get back to you, or I can give you pre-release of it. If you ask, okay, so what's the main difference? It's slower in certain ways, because the task was not to use the tricks. So if you imagine, let's say, even basic problem that you want to evaluate the semi-definite constraint, so you want to sum all the matrices which are sparse. At least there wasn't any MATLAB command for that, so you had to sum one after another, and that's obviously much slower than if you can do it something clever. So somehow to speed it up a little bit, we wrote two max files. One is for this summing matrices, one is somewhere inside for evaluation of Hessian, but basically there are equivalents and written in pure MATLAB, and it's really quite pure MATLAB code. All right, okay, I'm running slightly late. So what I wanted to do is to explain briefly the algorithm and show you demos. Let's see what I can manage. But basically the algorithm is based on something which could be called generalized augmented Lagrangian method. You will see in a little bit what I mean with that. And a special choice of something called penalty barrier function. And it has a relatively long history. But the first two links were for convex programming, and it was Michal Kočvara and Michael Stingel who changed it for SDP. Okay, maybe this slide shouldn't be there at all, but basically, if you have feasible region, infeasible region, the idea is, okay, you can have something like classical barrier approach, that if you are approaching the boundary, you somehow increase whatever and you avoid the boundary, or you can have penalty approach from outside. And this uses something specially constructed penalty barrier, which is kind of in the middle. In fact, it's glued together piece of logarithm and piece of quadratic function. Anyway, if you look at the algorithm, so this is, let's say, the original formulation you have, user input problem. Now we apply the penalties. You can see it as kind of scaling. The idea is that the solution for the original problem and for this new problem with the penalty barrier functions is the same. You didn't change the solution. You just changed somehow how the boundary looks, kind of. When you have this, you apply something which could look like augmented Lagrangian method, but it's not augmented Lagrangian method, so we call it in the paper generalized augmented Lagrangian method. Basically, you build kind of Lagrangian from the functions, from the penalty functions. So you add estimated estimates of multipliers ui and capital U for the matrices. And then what you do is that you have outer loop, you solve approximately the problem where you fix the penalty and fix the estimate of Lagrangian multipliers, solve it approximately, update, and use the point to do it again with somehow tightened up penalty parameters. And inside, well, that's kind of Newton-ish algorithm. So you build, at each point you build quadratic model, you get direction, decent direction, you apply something like line search, and that's it. And inside, what you do is you need to solve KKT system, or if you have no equalities, ordinary Newton system, you need to watch inertia of the matrix, because especially if the system is non-convex, then you need to be a little bit careful. You get the solution, you apply line search, you get new point, and you do this looping till you get convergence. What might be interesting is what's so special about the functions, about the penalty functions. Well, there are plenty of properties which somehow describe the group of the functions which could be applied. With the matrix one, the idea is that you somehow penalize the eigenvalues kind of directly. If you do eigenvalue decomposition of the matrix, you would penalize the eigenvalues and put it back together. But with special choice of the penalty function you use for penalization of the eigenvalues, you actually avoid the decomposition. So it's kind of implicit formula. The derivatives will look pretty crazy, but it's computable and everyone is happy. So, quick demo. Let's see how far we can get. So it's MATLAB. First you need to do is obviously to get to the right directory and add it to the path. So to the path edit. So now it works in the way that you define a structure which describes your problem. I will soon show you how it looks. Then you create the problem through PenLab, and then you say, solve it. It probably doesn't look so great with a big font, but basically here you see the outer iterations and that you are converging. This is just a toy example. And we created a couple of interfaces how to do it. So basically it's always how you create the structure where you put all the information about the problem, and then you create the problem through PenLab and solve it. So let's say if you have NLP, ample problem, you can create the structure, you can say create the problem and solve it. If you have SDP, then there is a sparse SDP A format file reader. You create data, we just say the matrices and how it looks. You create this structure which defines the problem, and you run Penlab to create the problem, and finally to solve it. So what I wanted to show you is that it's hopefully relatively easy to use, especially if you have format which matches the problems which we thought people might want to solve. If you want to look at the problems, so this was the first problem it was solving. You can recognize ample here, ample language. So how it would be coded to solve it directly without ample? Well, you create structure like this, and basically you say, well, it should have two variables. There are lower bounds on variables, upper bounds on the variables. Then you say that you have two nonlinear constraints. It's equally, it has lower bounds, and then you provide all the callbacks in this case, which defines the problem. Okay, And if you look to polynomial matrix inequality thing, which we thought how it would look, again, there are some comments which describe how it looks. So we have this kind of problem. It's the same as, or very similar as you saw on the slides. So we assume something like quadratic objective, some linear and box constraints, and finally matrix constraints, which are given as a combination of given matrices and x to the power of certain multi-index. And if you create this structure, again, you call just penlab, create the problem, penlab solve, and that's it. So I'm not sure if this was actually useful because it was quite quick, but hopefully it should show that the program should be relatively easy to handle, maybe. So if you want to try it, please do it, and we will be delighted to hear your feedback. So I'm getting to the end. So what are the future plans? Well, one of the plans is to add direct handling of second-order conic constraints to the pennon, first to the original pennon. For NAG pennon is tasked to catch up with the main pennon, with the original pennon, and with penlab, well, first of all, to release it. That's the first thing we want to do. Publish the report, and there are plenty of things we could do about it. One of these would be, as I said, it's written in MATLAB. It has certain limitations. So one thing I would like to see there is that there will be automatic binding to the libraries, either to the original pennon or to the NAG pennon, that suddenly if you find out that your problem is too big or too slow to compute with the MATLAB, you could switch like this to the implementations in compiled languages, and it would run much faster. Anyway, if you have any questions about this particular thing, you can always catch me on email or ask me here. If you have any questions in general about NAG, or for example you want to try that, you want to have trial license, just don't hesitate and write to support at NAG. And yeah, otherwise, thanks for your attention.
Okay, are there any questions? Yes, please.
How do you solve your linear equation?
At the moment, if there are equalities, then it's direct method used in MATLAB, so LDL, which is I think based in recent MATLABs on MA57, 57. And if it's without equalities, then you have just Newton system, and then it's called Cholesky. And in addition to that, if you don't have equalities, you can also switch to iterative methods, which actually helps quite a lot.
Yeah.
In certain cases.
That's the point. When the problem is big, that's impossible to use the direct method to decompose the matrix.
Well, it depends what kind of problem we are talking about. NLP problems can be indeed big, that this matrix is big, but in SDP problems you would usually hit the boundary before you get such a big matrix that you cannot solve it, because it would be super slow when you actually compose the matrix, which might be more expensive than solving the system. So yeah, but there are tricks that if you use iterative methods, then you can avoid building the matrix, which is the expensive thing, and it actually runs quite fast. But again, this MATLAB code I presented is meant more for testing, that people get feel how to solve or play with NLP SDP problems, and yeah, rather than super big problems.
Okay, many thanks.